Hello students, in today's session we will discuss about the state space analysis. So in this session we will have a introduction to the state space analysis. This particular topic is very important in modern control theories as it provides a powerful and flexible framework to model, analyze and design the control system, especially when dealing with multiple input, multiple output and complex dynamic system. We will explore the basic concepts, advantages of state space over the classical methods, and we will see how to represent a system using state variable. So in all of the previous approaches that we studied, such as transfer function based method, we assume that the initial condition of the system is 0. But in reality, this is not true for any practical system. Practical system often starts with some initial energy or state. For example, a motor might already be spinning or a tank might already contain some fluid. So the classical methods we have covered so far, like RH criteria, root locus, Bode plot, polar plot, Nyquist plot, those are mainly designed for single input, single output systems. In these methods, the transfer function is defined as the ratio of Laplace transform of output to the Laplace transform of input, assuming all initial conditions are 0. But when we need to handle systems with non-zero initial conditions, we want to analyze the multi-input, multi-output systems and study systems with more complex internal dynamics, we turn to the state space approach because it can represent the system at any state, whether or not it starts at rest. The state space approach offers several important advantages over classical method. Like first, it can be applied to wider range of systems, whether they are linear, non-linear, time variant, time invariant. This make it very flexible and powerful for modern control system design. Second, any nth order differential equation describing a system can be converted into a state of n first order differential equation. So this makes the system easier to model, analyze and simulate. The third advantage we can say, state space analysis is a time domain approach, which means we can directly study how the system behaves over time. It also suitable for digital computer computation, which is essential today for simulation and controller design. Fourth, using the state space method, we can design systems for optimal conditions by defining a performance index and finding the best controller to achieve that index. And also, the state space approach is computationally simpler in many cases, especially when the Laplace transform methods becomes difficult or maybe sometimes almost impossible to apply. So state space analysis provides us with a general, versatile and practical tool to handle complex systems that go beyond what classical techniques can easily address. So let's now look at some basic terminologies used in state space analysis. The first important term is state variable. A state variable actually refers to the smallest set of variables that can completely describe the state of the dynamic system at any given time. Or in other words, if we say, once we know these variables at a certain instant, along with the input, we can determine the future behavior of the system. We normally denote state variables as x1, x2, or x1 dot, x2 dot, like this. And also it is important to note the state variable don't have to be quantities we can physically measure or observe. They simply need to represent the internal condition of the system that determines its future behavior. Next, let's define the term state. So the state of the system refers to the smallest set of state variable such that if we know the values of these variables at some initial time, say let's say time t equal to 0, along with the input of the system, we can completely determine the future behavior of the system at any time instant that is greater than t0. This means the state captures all the essential information about the system's past that is needed to predict the future evolution. In short, we can say that if we know the states for time t equal to 0 and the input, the system entire response can be determined. Now, there are two more important terminologies. The first one is state vector. So if n state variables are necessary to describe the behavior of the system, we can arrange those variables as a component of vector. This vector is called state vector. Now, since let's say the state vector has n components, these variables can be thought of a point in n-dimensional space. Like for example, in this particular figure, a two-dimensional space is shown to us. And this particular space is called as state space. Each point in the state space corresponds to a specific condition or configuration of the system at a given time. So we can say that state vector represents the internal condition of the system at a moment in time, and the state space represents the set of all the possible states of the system that system can take. Now we can observe from this particular figure, we have a multiple input, multiple output system. The inputs are defined as U1, U2, U3 to UM. So we have M number of input. So the U, if we represent the U as a M cross 1 vector, it is defined as a input vector. In the same way, we have a multiple output. So there are output from Y1, Y2, Y3 to YP. So if we represent all the output as a vector, it is known as a output vector of P cross one dimension. Then the complete state space model can be defined using two equations. One equation is x dot is equal to ax plus bu. In this particular equation, the x dot is differentiation of state variables, whereas a is system matrix with a dimension of n cross n. Then x is defined as the state variable vector, and then the b is defined as the input matrix of variable n cross m. And u is defined as the input vector of dimension m cross 1. Similarly, the output vector y is equal to c multiplied by x plus d multiplied by u. All these multiplications are matrix multiplication. So c is our output matrix of dimension p cross n, and d is our data transmission matrix of dimension p cross m. Now these equations can also be represented as a block diagram. So let's say if you want to represent these two equations or the state space model as a block diagram, we can represent it as like, we can start with a integration block. So the input to the integration can be the differentiation of a state vector, and we will get the output as a state vector. Now a summing point can be added at the input side because we want to realize the equation x dot is equal to ax plus bu. So the a gain is multiplied with the x and it is given to the summing block. And then a input with a multiplication of b and u is given to the summing block again. So this particular system that we are seeing right now, it is representing the x dot equation. Then further, we can multiply this x with the matrix C, and it will be added with the input multiplied by matrix D, and it will be added with the summation. So this complete block now represents the output y. So this complete block now we are having is actually representing our state space equations or state space model. So In this particular session, we have covered the basics about the state space model, the terminologies of state space representation, and the advantages of state space representation. So, thank you for your attention.